We now look at establishing DSL networks with PPPoE as an alternative WAN technology for enterprise networks. The application of DSL technologies relies strongly on the existing telephone infrastructure that is found in almost every household and office globally. With the continued development of newer DSL standards allowing rates of up to 100 megabits per second, the application of DSL as a WAN technology for home and enterprise remains firmly valid. Traditional DSL connections were established over legacy ATM networks. However, Ethernet has continued to emerge as the underlying technology on which many service providers establish their networks, and therefore knowledge of PPPoE technologies remains valued for establishing DSL connectivity at the enterprise edge. So upon completion of this section, it is generally expected that trainees will be able to describe the PPPoE connection establishment process as well as configure a PPPoE session. DSL represents yet another popular form of WAN-based technology that makes use of the existing telephone network infrastructure to data communications beyond the physical boundaries of the typical enterprise network. It may be implemented pretty much anywhere that there is a telephone network and an exchange station that is capable of supporting the equivalent data that is represented by the digital subscriber line access multiplexer, and as such allowing small offices and enterprise businesses alike to make use of the technology. There are various forms of the same technology, with the common form being asynchronous digital subscriber line, or ADSL for short. However, for businesses, the capacity of ADSL can be understood as often limited. However, with forms of DSL technologies such as very high digital subscriber line and now VDSL2, the future for DSL-based technologies are likely to remain a viable solution for many enterprise-based networks. PPPoE is used to support the transmission of PPP packets through encapsulation within Ethernet frames that allow the data to be transmitted over broadband technologies such as DSL. In doing so, features such as authentication can be supported. In enterprise networks, a router operates as the gateway for the network and establishes a session with the service provider. This is achieved using PPPoE to carry PPP-based authentication from the router to a PPPoE server, that is also commonly referred to as a Broadband Remote Access Server, or BRAS, to perform the authentication and permit connectivity. The DSL modem provides the modulation of the signal over the telephone line to the DSLAM, where the signals join many other signals and is forwarded over the link to the intended destination. We can understand the PPPoE process based on two stages, the first being the discovery stage and the second being the PPP session stage. The activation of a session first relies on the discovery of the BRAS, with which a session is initially built. In order to support this discovery process, PPPoE uses four packet types in the form of the PPP Active Discovery Initiation, or PADI, Discovery Offer through the PADO packet, Discovery Request through the PADR packet, and finally the Discovery Session Confirmation, or PADS packet. The remaining packet type is the PADT, or PPPoE Active Discovery Terminate packet that will manage the termination of an established PPPoE session. We now take a look at the PPPoE session establishment process to better understand the role of each of the protocol packets introduced. We start here with the PADI packet type that initiates the discovery stage. In this example, we can see and understand that RTA is used to represent the customer edge and various servers to represent the number of BRAS devices with which the session establishment is possible. RTA is expected to firstly identify the MAC address of the server and establish a PPPoE session ID to begin creation of a unique session. In order to achieve this, a PPPoE Active Discovery Initiation, or PADI packet is generated containing service information required by the client. The information is sent as a broadcast and so will be received by any BRAS considered in range. Receiving servers will make a comparison of the requested services to the services that they can provide. For those servers that are able to support the services required, a PPPoE Active Discovery Offer, or PADO packet is generated and returned to the sender of the PADI packet, which in this case is RTA. In this instance, multiple offers are received by RTA. The PADO will be received by RTA and one of these servers chosen based on either the server name or the services that are being offered, to which a PPPoE Active Discovery Request, or PADR packet is sent as a unicast to the selected server, which in this case is server A. After a PADR packet is received, the server will begin to prepare the unique session that will be generated between itself and RTA. It is at this point that the unique session ID is created and sent to RTA as part of the PPPoE Discovery Session Confirmation or PADS packet. It is sent in response to the PADR, by which point both RTA as the client and server A are now aware of the Ethernet address of the peer, and following reception of the PADS packet, will also both be aware of the current PPPoE session ID. If there are no errors, RTA and the server will move into the PPPoE session stage. Following the discovery stage, we find the PPP session stage is started, and basically follows the same PPP process, beginning with the LCP negotiation and proceeding through the same established authentication and network phases as were covered in the section focusing on PPP. One of the key considerations that must be taken into account when dealing with PPPoE is the need for support of the extra payload that is incurred. The maximum supported size of a packet is typically 1500 bytes. However, when including the additional PPP and PPPoE header information, this swells by an additional 8 bytes, which will cause fragmentation of the packet to occur. It is therefore necessary that the maximum receive unit be listed as 1492 bytes to limit the size of the packet and accommodate for the additional overhead. It is possible for the PPPoE session to be terminated at any time by either the client, which in this instance is RTA, or the server with which the session is established. This is achieved through the PPPoE Active Discovery Terminate packet, or PADT, that will contain the session ID of the session that is to be terminated. In order to configure the PPPoE client, there are 3 individual steps that must be performed. The first involves configuration of a dialer interface that is responsible for performing PPP on demand establishment of a session connection, following which the dialer is bound to the interface over which the negotiation is to take place, and finally is the establishment of a static route to allow select traffic to initiate the PPPoE session. We start here with the creation of the dialer interface, in which the shown commands are applied. The configuration starts with the creation of a dialer rule under the dialer rule view that defines the packet types that are supported by the dialer, which in this case are IP packets. We then must create the dialer interface and apply a username which represents the host, such as host A, when establishing a PPPoE connection. The dialer group is a group defined by the dialer interface, and the dialer group number must match the number that was set for the dialer rule, which in this case is 1. A dialer bundle is then created that is used to take the dialer interface on which dialing parameters are set and allow physical interfaces to be dynamically bound to this dialer interface. We then implement authentication for the created dialer interface using chat, for which a user and password are defined, and implement the IP address PPP negotiate command in order to enable the IPCP to obtain the IP address from the remote device, which in this case is RTB. Once the dialer interface has been created and the general configuration parameters have been configured, we next need to complete the binding of the dialer bundle to the interface over which negotiation of the PPPoE session is to take place, which in this case is interface gigabit Ethernet 0/0/1 of RTA. We therefore must firstly go to the interface view for this particular interface and implement the command PPPoE client dial bundle number, for which the dial bundle number used should match the number of the dial bundle previously created. What this basically does is binds the dial bundle to the interface. We also find the on-demand parameter included here, which means the PPPoE session will only establish when activated by traffic being received on the interface. It may be that this represents a secondary connection to back up a primary connection that will be used to route traffic. However, should the primary route fail, we would wish that a PPPoE session be established to take over and prevent downtime to external resources. How we provide that backup route is through the use of the IP route static command, in which the last resort address of 0.0.0.0 is used. This represents any network and applies in the event that no other longest match route is found. In such cases, traffic should be forwarded to dialer 1, which is now bound to interface gigabit Ethernet 0/0/1. If the on-demand parameter is not used, the PPPoE connection may be used as the primary route. Following the configuration of the dialer interface, we can use the display interface dialer command to view the current status of the dialer interface that is now bound to interface gigabit Ethernet 0/0/1. We find as a result that the dial interface is up and running, to which an IP address of 192.168.10.254 has been negotiated. We will also find that LCP is considered open, which shows that a configure ACK packet has been received from the peer, and also that IPCP is open, which means that network layer protocol packets can be successfully sent over the link. Another display command that may be used is the display PPPoE client session summary command, which displays the information for the PPPoE sessions on the client, which in this case is RTA. We demonstrate two examples of the output that may be viewed, the first representing the configured PPPoE dialer that is bound to interface gigabit Ethernet 0/0/1, but here we find the state is currently idle. This represents a situation in which an attempt to establish the PPPoE session has not yet been made. It may also be possible to view a state of PADI that represents the client has started the discovery stage by sending a PADI packet, or we may also see a state of PADR that shows the discovery request packet has been sent also by the client. Ultimately, however, we should expect to see the status of up, which demonstrates the PPPoE session has been successfully established. The implementation of the PPPoE session that has been demonstrated throughout this section has been done so based on a typical lab environment to give a clear understanding of the stages that are involved in the PPPoE session establishment. In real-world applications, however, we will find that hosts located within the enterprise network are supported by private networks that are unable to exist as part of the public network domain, and therefore require addresses to be translated by the gateway, which in this example is also the PPPoE client. It is at this point that the PPPoE client would negotiate not only a session with the PPPoE server, but also for a public address to be used on the outbound interface. Traffic being received from internal hosts such as host A and host B will then need to have their addresses translated to the addressing that is associated with the outbound interface to support transmission over the established PPPoE session. How this translation is achieved is covered as part of the next section. So this brings us to the summary for this section, in which we have just a couple of questions here. The first asks, why is it necessary to reduce the MTU-MRU size of PPPoE packets? Well, we will generally find that the packet size is set as 1500 bytes, which is the maximum supported size before fragmentation will occur. When PPPoE is implemented, the packet size is increased by an additional 8 bytes. It is therefore necessary to reduce the general MRU size that is received from the peer to 1492 bytes. This is negotiated during the LCP process. What is the purpose of the dialer bundle command when establishing the PPPoE connection? Well, the dialer bundle, if we recall, is basically used to bind the physical interface to the dialer interface, with which the dialer parameters are associated in order to establish the PPPoE connection.